Next up is question 6 that says find parametric equations for the ellipse whose rectangular equation is given by x over a squared plus y over b squared is equal to 1. All right, now let's first go back to question 4b where we were matching parametric equations to curves. And we had that x is equal to 2 cosine t and y is equal to 3 sine t. And we argued there that this gives us a parameterization for this ellipse centered at the origin with semi-minor axis of 2 and semi-major axis of 3. And we argued that by appealing to the Pythagorean identity, right? So cosine t is x over 2, and so cosine squared of t is x over 2 squared, and likewise sine squared of t is y over 3 squared, and this is equal to 1, and this is an equation of the ellipse centered at the origin with semi-minor axis of 2 and semi-major axis of 3. All right, so now for the more general case, we can go ahead and proceed as follows. Okay, so for this ellipse, and notice if A is larger than B, right, then the semi-major axis will lie along the x-axis as opposed to the y-axis. But in any event, the idea here, just as we saw up above, right, so in this case A is 2 and B is 3, and see A acts as the coefficient of the cosine wave and B is acting as the coefficient of the sine wave. So for the general case, we can set x to A times the cosine of t and y to b times the sine of t, right? So the amplitude of x is A. So as we let t increase, x is just going to oscillate between positive A and negative A. And the amplitude of y is b, and so as we let t increase, y will just oscillate between b and negative b. All right, and we make one trip around, right, over the period of these waves, which is just 2 pi units. And we're going to move in a counterclockwise fashion, right? Why? Well, because when t is 0, x is a and y is 0. So we're right here at the point a is 0 when t is 0. And then in the next few moments, x will decrease, meaning we're moving to the left, and y is going to increase, meaning we're moving up. So we're moving to the left and up, giving rise to a counterclockwise orientation. All right, now let's go to Desmos real quick. I want to show you something. So here's the ellipse equation, and here I just have set a to 1.88 and b to 1.03, and then I have a cos t. Here my parameter for the slider here is c, since I've already used a and b, and then I have b sine c, and we're going to let c run through the interval from 0 to 2 pi, and when we do that, we see that we're moving in a counterclockwise fashion, and we complete one trip in 2 pi units. Okay, and so changing our value of a and b, right, it's just going to affect the shape of that ellipse. But in any event, right, this parameterization is doing the job. Note that if we set a and b equal to one another, we get a circle. And now we're just back in the case of uniform circular motion that we've been looking at in these last couple videos. All right, well, that's a good place to stop. I'll see you in the next video.